thank you for coming. And so today I'll be discussing the influence of gravity waves from small islands, the ocean, and subject to your atmospheric circulation. And this is actually a project that I started the last couple months in my postdoc, so almost, I guess, 4 years ago, more than 4 years ago, almost 5 years ago now. And finally, we wrote up and finished and packaged, and now it's finally going to be published with collaborator of mine from NASA. So I'll first give some motivation and discuss some background on gravity waves, and then show some results. So the motivation, so this is a map here of the southern hemisphere. We have Antarctica here, and we have 40, that's south and 60 south. Not much land, there's a little bit of South America here, New Zealand here, otherwise there isn't much land in this latitude band. However, there are a series of islands, so here, that are present here in this latitude band, between 40 and 60 south. Particular islands I'll be talking about in this log are South George Island over here, Heard Island, and Kerguelen Island. So these islands are all very small. In South George Island, I'll show a picture of this island in a minute, but if you take all the land area in South George Island and condense it into a circle, the circle would have a diameter of 80 kilometers. So these are small islands. However, some of these are mountains, in particular South Georgia, Kerguelen, and Heard Island, are mountainous, and they'll show it now. So this is a picture of Kerguelen Island from some sea. So you can tell there's a big mountain right smack dab in the middle of this island. High elevation, nearly 2 kilometers above sea level. So this surface area of this island is 7,200 square kilometers. So if you take all the surface area, take the area of land in this island, pack it into a circle with an 80-kilometer diameter, so it's not a very big island. Pretty much any climate model that exists anywhere in the world, even as of today, does not resolve this island explicitly whatsoever. Maybe there's a tiny bit of something, but it certainly doesn't. You won't get any mountain like this. Even a weather forecasting model will have even a 9-kilometer or 10-kilometer resolution. A weather forecasting model will have lots of trouble explicitly resolving.
Is it inhabited, the island?
This one actually, I believe, is. I'll show you. I don't know. This one is not. This one has a weather station. This one has a scientific base, but no permanent inhabitants. This one actually has. I think it's really live here. So this is one of the other islands, South Georgia Island. This one is even taller. The mountains here in the middle of the island. Even smaller area, less than 4,000 square kilometers. You take all this down and pack it into a 70-kilometer circle. It's not a very big island, but it has clearly large mountains, which can launch gravity waves. And this is the third island I mentioned, Heard Island. This is actually almost 3 kilometers, and this is looking at from the sea. Basically, this island is one big mountain. If you go, if you stand at the top here, if you stand at the top of this mountain here, this is a topographic view of this Heard Island here. You stand on the top here and also the peak. You go 28 kilometers in any direction, you're in the ocean. So basically this island is a mountain that sticks up out of the side of the ocean, and that's all there is to this island. So it's very tall, almost 3 kilometers above sea level, but very small. I mean, this is basically the average from here to here is like 20 kilometers, 25 kilometers. So these are all very small islands. The wind speeds in the Southern Ocean are very strong. You have wind speeds in climatology of 10 meters per second, 12 meters per second winds going over these mountains, launching waves. And the question is, and we see these waves. This is a satellite image, not from a different chain of islands. These are sandwich islands. These are right next to the South George Islands, or fairly close to them. And you see in the cloud field, you see these undulations. Right in motion, we have the advanced clouds, and at the center we have lack of clouds, relative lack of clouds. You see this characteristic V-shape, which is the hallmark of internal wave. This is from looking at clouds. You can also see these gravity waves in satellite imagery of temperature. What I'm showing here is temperature perturbations associated with Heard Island. This is one right here, Kerguelen Island is right here, and South Georgia is over here. And this is temperature perturbations in the upper stratosphere. So this is from an air satellite looking at the upper stratosphere, or sort of mid-upper stratosphere, 40 kilometers.
So an island that's about less than 2 kilometers, it forces the flow at 40 kilometers?
Yeah, it forces waves that propagate, and the wave propagates in all directions.
Ratio 1 to 20?
Sorry?
It's generally a ratio 1 to 20 in heights.
What do you mean by that?
The height of the mountain is less than 2 kilometers. According to an island.
Yeah.
And you say it's upper stratosphere, which means what, 40 kilometers?
Yeah. So the waves are generated in the boundary layer, but then they propagate in general in all directions. So I'll actually show the velocity of gravity to a couple slides. But yeah, these waves propagate in general in all three directions: zonal, horizontal, and vertical. And here you see the impact of these islands at temperatures 40 kilometers above the surface. So this is a wavelength that has a wave function that peaks 40 kilometers above the surface. So you can see, and this is just a climatology, or this is just a snapshot. This is like the 10th of August 2003, the 6th of September 2003. So these are just snapshot of one day. And you see the characteristic V-shape, each of these islands. Warm, cold, more cold. And if you look at the color bar here, 4 Kelvin, plus or minus 4 Kelvin associated with these islands. So they have the temperature variations, they're technical. I mean, from here to here, there's a 8 Kelvin difference in temperature associated with the rising and sinking motion associated with these waves. So we know these waves exist. There's no shortage of evidence that these islands launch gravity waves. And the question is whether these waves impact the southern hemisphere atmospheric circulation. And that's sort of the question that we want to address. For those of you who don't remember what the stratosphere looks like, what the stratosphere actually is, so I'm showing here just as some background is southern hemisphere view of the southern hemisphere is on the right, latitude versus height, latitude versus pressure, so the troposphere is basically from here and below, stratosphere is from here and above. What I'm showing here is zonal wind, zonally average zonal wind, June, July, August, in the period 40 analysis data. So the troposphere is from here and below, and stratosphere is here and above. So in the southern hemisphere, in the subpolar latitudes, we have winds that are 100 meters per second in the climatology, so very strong winds in midwinter. And these winds in midwinter weaken as you go into spring. So this is June, July, August. This is the same latitude versus height in September, October, and November. So winds are weaker. Also, the peak in the winds shifts down into the mid-stratosphere as you move into spring. And then by summertime, these winds are replaced by easterlies. The strong winds in the subpolar stratosphere strong westerlies are replaced by easterlies. And so this is the sort of climatological seasonal cycle in the southern hemisphere. And it turns out that most models have issues representing this seasonal cycle. So what I'm showing here is a transition to easterlies at 60 south. So if you focus here on 60 south, which is right here, if you look at the day as a function of height, so we're going from the mesosphere down into the lower stratosphere, the day of the year in which the winds transition from westerlies to easterlies. So the winds, the black here is reanalysis data, you're at 40, a different analysis product and stuff. So the winds transition to transition to easterlies in the lower mesosphere around end of October, beginning of November. As you go further down into the mid-stratosphere, the transition to easterlies around mid-November or so, and then in the lower stratosphere, the transition to easterlies in sort of mid-December. So these are the black lines for observations. If you look, all these models here are just different models. And these are models that basically hope have good representation of the southern hemisphere stratosphere. These are models that all have correct chemistry. They all have a well-resolved stratosphere. They're sort of the best we can hope for. And systematically, that's a couple of exceptions. Almost every single model has a delayed breakup. Basically, the the transition each release occurs an average about 3 weeks too late, 3 weeks to a month too late. So pretty much every model out there has a spot, has a size, and basically not a single one of these models actually represents these islands whatsoever. These islands are ocean for all intents and purposes. There's no gravity waves launched by any of these islands that I mentioned before. They're completely missing. Because of the way the gravity wave scheme historically has been parameterized. So the question is, I mean, it's been suggested or proposed that if we add in gravity wave flux from these islands, it could help. This bias, there's two papers. This is sort of a modeling perspective, more idealized modeling perspective than what I'll describe, and this is an observational paper that showed that these islands actually do generate wave flux. And so we'll explore whether this actually is true or not. And the other piece of information that we know that there's an issue with models is looking at the analysis increments from the reanalysis product. So basically, you start with the reanalysis product. Reanalysis has a model underneath it. The model has its climatology, and in an ideal world, the observations that you feed into the model will just sort of tug the model towards reality. Will not introduce any systematic westerly tendencies or easterly tendencies. There'll just be a tug in any given day towards what actually occurred in that particular day. But the climatology will not change. That's in an ideal world. In practice, in the subpolar stratosphere, so this is 60 south, in the subpolar upper stratosphere, there's a systematic tendency from the analysis increments. In other words, the observations are tugging the model away from climatology. The model wants to have stronger winds up here. The observations are tugging the model back towards having weaker winds. And in this systematic way, average over many years, many days, you find that there's a 2 meter per second, 1.5 meter per second consistent tendency that has to be introduced into the model in order for the reanalysis product to match observations. So the implication of this is that there's missing drag. Some physical process is missing in these models. And it's been proposed or suggested that this missing physical process are these islands. That if only we added these extra islands in our models, or if we added the gravity wave flux from these islands into our model, we can try to fill in this gap and have a model with better climatology. And if the model has better climatology, we won't have to do this kind of, we won't have to pretend this momentum in a sort of physical manner. This is one particular reanalysis product, so now 2 reanalysis. If you look at other reanalysis products, you find a similar bias. So reanalysis products are moved the momentum from the southern hemisphere or stratosphere to balance the momentum budget. So clearly we're sort of making up momentum. So we're not really solving Newton's equations anymore. So question, is there some sort of missing physics there?
So you're doing it in the reanalysis?
In the reanalysis, yeah. So in other words, the model has its climatology, and ideally all the observations have to do in the reanalysis is basically tug the model towards reality for that particular day. But if
the model produces too large losses speeds?
The modes are too strong in the model, yeah. And so the observations systematically have to tug them all towards weaker wind speeds.
Chaim, if you have waves, it means that the stratification is stable about this. So what is the mechanism of drag that...
I'll try to get to that in two slides. Two slides. So that's the suggested that these models are systematically missing these gravity waves from these small islands because they're just so small they can't be represented. So I'll discuss how gravity waves actually work in models. There's a model I used for this study. It's a geosynchronic. It's a model developed at NASA. It sort of has a dynamical core, coupled to the dynamical core moisture and mixing, surface processes, radiation, all things, correction schemes, everything you expect to see in a common model. These particular experiments all have stratospheric chemistry as well, so the best we can hope for the southern hemisphere stratosphere. And these are all done, relatively coarse resolution nowadays. This is on the coarser side of things. Usually these by 2.5 degrees, but we have almost all stratosphere at least. And this model also has a 2 to 3 week breakdown bias, the wind's transition to easterly is 2 weeks too late.
I have a question about the missing physics. It has been known that a big missing physics is the too little amount of simulated clouds in the southern oceans that absorb too much solar radiation, and had too little, and therefore it has too little meridional temperature contrast in the lower troposphere, in the ocean. So my question is, how do you get this part right, or is it still?
Actually, I haven't actually looked at the cloud fields. I know there are biases in this model in the stratus text. It doesn't do a very good job with the. That's further closer to the equator. The stratus text off the stratus text.
In the higher latitudes.
Yeah, high latitudes. Yeah. So high latitudes, I'm not familiar with whether there are biases. Presumably there are biases.
It's definitely a big hole in the missing physics.
Yeah.
And if you're talking about missing physics, you need to account for that also.
I agree that the conclusion of the study, I think we'll get to in maybe 20 minutes, is that these islands help, but they're not the full. But they're clearly by no means the full answer. So there are other processes that are likely missing. So I think I agree with you that it could be that there could be cloud biases. So when you have a mountain here, it launches, it perturbs the flow of air over the mountain. You end up with a series of, in this case, trough lines that oriented into the wind. So if your wind is pointing in this direction, the trough lines that are gravity wave are pointing up into the wind. And the group velocity, the direction of the group velocity is actually pointing in this direction. So the group velocity is actually pointing upwards and into the wind. The individual crests of the wave turn out to actually propagate at a 90-degree angle that actually propagate into the mountain, which is an interesting property of internal gravity waves. The important point is actually the group velocity. Group velocity is up and into the wind. And which allowed these waves to propagate all the way into the stratosphere. And specifically, just for to answer your question, so if you have a mountain here, here's your mountain. So the air motion will go up, has to go up and over the mountain. It gets depending on the Freud number, but in the case where the Freud number is such that you have waves go up and over the mountain, and the group velocity, so the wind speed, ambient wind speed is this blue arrow here, ambient wind speed is pointing in this direction here. Group velocity is shown here with this yellow arrow, it's up and into the wind. The phase propagation is this green arrow here, just down and into the wind. And if you actually look at the wind perturbations on either side, here you have a deceleration of the wind, so your zonal wind speed relative to the ambient wind speed is a weaker wind speed, so U prime is negative, you have a sort of deceleration of the wind. But you also have rising motion, W prime is positive, your relative rising motion is in distribution here, so you have U prime, W prime is negative. And also in the lee of the mountain, here you have actually some acceleration of the flow. U prime is positive, in this case W prime is negative. Basically, you have downward motion and you have acceleration of the zonal flow. So both the leeward side and also the moonward side, your product of U prime and W prime is negative. So that's a key point here. U prime W prime is negative, which allows, if you have winds, allows for the winds that are higher up in the atmosphere, the momentum higher up in the atmosphere to be transported downwards, where it can be removed from the atmosphere by the mountain itself. So the key point of this slide is that basically you have momentum way up here in the stratosphere, you have your mountain down here, and because of the way these waves are oriented, you can basically take the momentum that's way up here in the stratosphere and bring it down to the surface and damp it out.
Is the change in U mainly in response to the change in elevation or you increase the potential energy.
Yeah.
Therefore, you decrease the
kinetic energy.
and W has to be positive. So V prime has to be negative, it must be negative.
Yeah, I got it.
Chaim, these are Lie waves, what you are describing, aren't they? And for Lie waves, if I remember correctly, we have analytical solutions.
So if you have a single, if you have a single, if you have a single Gaussian, you're right. If you have a single Gaussian, I mean, if you imagine you have a single, if you imagine it looks like this, you can use it indefinitely, then you're right, there are analytical solutions. The confusion or the interesting aspect is when you don't have that time. I guess in principle you can decompose any weird sigmoid into a whole bunch of sines and cosines, then you get your solution. I think that the issue is there's also, if I remember correctly, I should review my notes, but in the case where you have a constant attack stability and constant wind speed, then you actually can derive analytic solution to the gravity waves launched by this mountain. If your run velocity or your stability changes with height, or if your wind speed changes with height, and also to account for the density effects with height, then you start needing quantization. But I guess So in practice, the mountain stays there, but the wind speed, the flexibility, and densities, density profiles will change. So pretty much every physics type step in your model, you have to solve. In general models, there's a single column. You basically solve for a single column how the group is basically the vertical component, the group velocity. You solve for that explicitly, and you usually solve for where the wave makes.
How do you have an explanation for the westward shift of the point where W prime vanishes as you go up higher? It doesn't occur over the crest of the mountain.
Yeah, so it has to do with the phase. There's a phase. Mathematically, if you solve for the group velocity in the phase,
it must assume something on the waves. It's not clear from just a decomposition into mean flow and perturbation.
Yeah.
Why, at least to me, maybe there is an explanation.
Yeah.
Why there is a
at least my thing is to ask if you're, the fact that the phase speeds and the velocity are pointed in these directions, that you can show analytically. And I think if that's the case, then at least I would think that this would have to be a part of that. In other words, if your phase velocity, if you're propagating energy lines like this, your fronts are propagating down in this direction, then shouldn't you expect?
But you can change all the arrows accordingly. Just
you could.
Plot
If your wind speed was in that direction, then if you have east and westerlies, then everything would be going the other direction.
No, if you keep it as westerlies and just plot the stream function as parallel to the topography, so the maximum deviation, if you will, occurs at the same point in X, then the results have a solution. The yellow arrow will probably up or down.
I guess I have to sit down then. I don't have to answer.
It doesn't stay the same X. It does not stay the same X.
I understand why. You understand?
Yes. So in terms of the models of these, if your mountain has a characteristics length scale of, let's say, 40 kilometers or 20 kilometers for some of these islands, and your model grid spacing is 100 kilometers or even more, or 200 kilometers or even 50 kilometers, you clearly aren't resolving any of this. Everything has to be parameterized. And it turns out if you run a high resolution model, if you run even a weather forecasting model, say 10 kilometers or even 10, 15 kilometer, and you compare the wave flux generated at 50 kilometer to 5 kilometer, 10 kilometer, it turns out you don't converge the actual solution until you get to about a quarter, even less than a quarter, even an eighth of the characteristic scale. So if this your mountain here is a 40 kilometer characteristic scale, you would actually need a model with a 5 kilometer resolution to even to resolve these waves explained. So the problem is actually harder than it looks. In other words, anytime in the next couple of decades, we'll need to have gravity wave conformations. Something it has to be included in a model, and it won't be included in the next 20 years because of this fact. And actually, there's a version of this particular model, the GeoCCM, run at 7 kilometer resolution. If you have 7 kilometer resolution, the wave flux through that is logography minus the actual logography. I'm sorry, this is a mistake here. It should be actual logography. So this difference here is what actually forces the gravity waves and the parameterization. And you see this big peaks here in the Andes, big peaks in the Antarctic Peninsula, over the Atlantic coastline. There's also large topographic variance. This is South George Island. You see nothing here. Bergeland's over here. Bergeland's right next to it. You see nothing. This is the default version of the model. Basically, if you just take the model straight out of the box, this is what it looks like. And there's basically nothing going on for these islands. So there's a gap in variance. But we know these islands generate gravity waves. So what we try to do is we basically hacked the gravity wave variance file for these islands. And we pretended these islands had more variance than they actually did using the scheme that we used. So here's South Georgia, there's Sherburne. We hacked the variance files to basically artificially enhance the gravity wave flux from these islands. So first of all, we did this in a bit of an ad hoc way, but the end result was we wanted something realistic in terms of the actual fluxes of gravity waves. So the way we actually did it in practice, we identified the maximum topographic variance from a high resolution version of the model, a weather prediction version of the model. And we then used this value of the corresponding grid point at the chronometer resolution. We also did the same thing, but multiply the magnitude of the variance by 5. And we also did the exact same thing for an at-on version of the model and also a cube sphere version of the model. So two different versions of the model. And the right change is what's shown here. This is the 5x for the biggest change. We started with this and we ended up with this. So the variance values at South Georgia and Bergeland Island are still smaller than anywhere over the Antarctic Peninsula or South Andes or Central Andes. But they're not noticeable. You actually see these islands.
So what you changed in your modified simulation is essentially added in the parameterization stage.
Yeah.
Why not just increase the size of the island? Make it 400 kilometers, see if you get what you want.
I mean, in principle, you could. I mean, you'd have to then hack the topography. You then have to hack the topography file as well. So you can, so there's just a couple of different ways to. Yeah, you said, yeah. In fact, that's essentially what we're doing. We're pretending these islands are bigger than they actually are. We're pretending these islands are at least a good box. And then once we make them a good box, we then give them the value of the variance that's not doesn't really belong there, but we're sort of motivated by what actually occurs when you go to higher resolutions. I mean, the ultimate reason why we did the thing that we did is actually mimic this. This is from this Hemisphere paper. This is the actual flux of gravity waves from Bergeland Island from I think that's a 4 or 5 year cometology. And also this is Bergeland Island, Berg Island, and just South Georgia Island. And the values of fluxes in the unit geometry. After you take this variance and multiply it by essentially multiply by the function protocol, you can see multiply by a couple of the factors, with the flux. We basically wanted to match these values here. So for the 1x case, we actually were a little bit below 1x experiments. Underestimate these values. The 5x experiments a little overestimated. So we're sort of straddling these values here, and that was sort of our guide, our goal was to match these values, and then once we put this in the model, then we can run the model and see what happens. Okay, so then get the results. So this is the actual photographic gravity wave, the control version of the model, meters per second per day. So south pole here, equator over here. So this is the flux that you see up here, the deceleration. These are gravity waves launched by Antarctica, by topography in Antarctica, that propagate upwards and weaken the winds up here into the subpolar stratosphere. We also have the Andes here. The Andes also launch gravity waves, propagate upwards. weaken the winds in this region here. And this is the updated minus control, and you can see here is the effect of Kerguelen Island. Sorry, this is South Georgia, this is Kerguelen. See that these waves add some extra momentum, actually add some extra deceleration of the winds around 55 and 50 south.
That's a drag.
Sorry, extra drag. And so the question is whether this actually matters for the southern hemisphere circulation. It turns out it does. So what I'm showing here is but it's a relatively small, modest effect. So this is the climatology of polar temperature, 75 south and polar temperature from February. It's a function of calendar month from January to December. This is in the model. This is in observations, analysis data from the upper troposphere down here, up into the upper stratosphere, mid-upper stratosphere here. And so you can see here there's temperatures here in the observations, about 185, 190 Kelvin in midwinter, and these temperatures rapidly transition to temperature to warming in springtime. And in the model, there's two biases. One is that the temperatures in midwinter are too warm, and then the transition to the warmer temperatures in spring occurs too slowly. So we show that here. This is the bias, the control version of the model. Temperatures in midwinter are too warm, and then in springtime they're too cold. The transition to each of these is too slow. And this bias extends into the lower stratosphere in summer and fall. This is the bias of the control version. This is the bias of the updated version. You compare these two, they don't look that much different from each other, so you can say, this whole exercise shows that it doesn't really matter all that much. Or maybe if you just pick a difference between the updated and control, you see that there's a difference. This is significant. It's about 2 degrees warmer in the lower stratosphere, updated versus control. So it does actually do something, but it's clearly not the full answer to why models have issues in this instance. So I showed you these results for the stratosphere. It turns out that this change in the gravity waves also impacts surface winds and tropospheric winds. So here's the surface wind speed in the control version of the model. We have winds over the Southern Ocean, over these islands that are 10, 12, 13 meters per second in the climatology. And of course you have storms that pass through and you have wind speeds that are double that. This is the control version, the wind speeds in the Southern Ocean, and this is the bias in the model. The winds are, first of all, too strong. You see that with this projector we can't really see much anything here, but these are 3 meters per second wind biases. The winds are too strong by about 3 meters per second over the Southern Ocean. And the winds are also slightly too far forward. The winds are, the peak in the wind bias is near 60 south, whereas the maximum wind speeds are 50 south. So you have a forward shift in overly strong winds. This is surface, and if you look higher up, 200 pascals, so upper troposphere, you see a similar bias. You have wind speeds that are too strong, positive biases to overly strong winds, and also winds that are too far forward. And so what happens when you make this change in the gravity waves? This is the difference between the gravity wave run and the control run. So after we add in these gravity waves, we decelerate surface winds over the Southern Ocean, which is a good thing for the model. And we also decelerate the upper tropospheric winds and also shift the winds a little bit greater. So these are all good changes for the model. Again, the bias, these changes are generally 20% to 30% of the bias. So it's not there's clearly more other processes besides this that are important. So this is the 1x version, this is 5x, and it just shows the different. When we have the 5x perturbation, the overly strong perturbation, they have a bigger change. Okay, so just a quick summary. Increasing the gravity wave drag on these islands does lead to a good surface wind and forming the 6 atmospheric circulation. However, the improvements are generally pretty modest. If you translate this to the analysis of increments from the analysis, you find out that they're partially filled in, but there's clearly other processes as well that are important. I think that's it. Thank you.
comment about southern ocean clouds was very interesting because, as you show here, there are multiple effects of the surface winds and the mutual effects of the temperatures. And you play with the wider spectrum of changing these just to get a qualitative understanding of making them like 20 times larger. And then
so I actually did a 20 times larger run. I stopped after 3 years because. So if you make it that as 20 times larger, you actually, I'll go back to the slide here. I'm just showing you the southern hemisphere. So if you make it 20 times larger, you end up getting colors that are actually, on the order of these reds here. And actually, if I show the northern hemisphere, show the Himalayas and the Rockies, you actually, you get a kind of color part where it's capture the Himalayas and the Rockies. And when you make these 20 times larger, you actually end up with like a Himalaya type perturbation. So that's something new. This was clearly not physical. So I did do a run for a couple of years and I stopped it, but maybe it would actually be interesting to see.
If you go back to the anomaly,
in the wind.
One of the last slides. The control minus observations. Yes, you see here surface winds. There is a very strong difference, and that so you need actually to accelerate, not to accelerate.
No. This is control by observations. In other words, the winds are about almost 15 meters per second in this region. It should be 12 or so.
That means that the
winds are too strong.
The control minus the simulations are so strong.
Yeah. So in other words, we need to begin the winds in order to.
So, how do models parameterize the drag of associated with gravity-related propagation?
So the way this model does it is basically a function that I think is proportional to this sigma, to this variance. It's also proportional to the buoyancy frequency, the wind, the density. There's a fudge factor, a tuning factor. It's also here as well. And you basically, the actual stress is essentially I think it's proportional to the square of this. So basically, it's proportional to all these factors. And so you can see it's after launch, you launch waves with that spectrum, and then you propagate it upwards. And then if the phase speed and the wind speed match, and the way it's breaking, that's where you remove the momentum.
So these are heuristic arguments that say that the drag should increase with the wind speed, the drag should increase with probably the height.
Well, in this case, these relationships are when you tell them analytically for very basic. These relationships are you can try analytically as well. But we're not actually resolving three-dimensional propagation of gravity groups. It's all done in a single column sense.
Right.
Very, very idealist way.
But the most you can get from such arguments is the general wave, or the general dependency. I.e., it increases with this, it increases with that, etc., decreases with that. But it's very hard to get the exact manner in which it increases. Linearly, quadratically, to the power of 1.2 or what have you. And even much harder than that is to say something about the coefficient.
Well,
I mean, you can say proportional, it increases with that. So how do they determine the...
Well, this coefficient is a tuning factor.
Is a tuning factor.
Yeah.
So why don't you increase it?
Well, then they increase the waves everywhere, which then leads to problems in midwinter. So there's basically a balancing act because if you increase the wave flux everywhere, then you basically warm everything. So you have nothing this size, so you make this bias worse. So it's a trade-off.
But you have probably 4 exponents in there. No? I mean, the assume it's all 1.
Yeah.
Maybe
physically should be. If you have a very simple case where these things are constant, you can derive the the waves analytically, and then if you increase these things by factor 2, then everything goes up. In other words, I think the linear dependence, I think, is physical.
Simple.
I think it's also physical. But yeah, I mean, in some sense, you want to keep the representation physical, but also, at the end of the day, there was a tuning factor. Which you can then think is the tuning factor.
So N is the buoyancy frequency.
Yeah, buoyancy frequency. Yeah.
And U is the wind speed, and rho is the density.
That's it, yeah.
And you probably have something that has to do with the originating factor, like you assume something on the island.
Yeah, this is like the variance file. The variance.
So did you assume a Gaussian of some sort?
You assume
Gaussian island? Or?
No. So there's within this E factor, you can actually decompose this effective wavelength. Which basically tells you this wavelength here. So, I'm actually thinking right now whether it's proportionate to the wavelength or the wavelength. But there is, in the case of analytic, if you solve this analytically, you can actually there is a dependence on the wavelength.
So you have an analytic dependence, say, for a Gaussian or something. For sinusoidal.
Okay. So in the case of the quantization, generally you ignore that. Part of the justification for what we did here, the question is, what we did here is sort of ad hoc and a little bit, maybe it seems a little strange. Like, why should we need to do all this in order to have wave fluxes that match this? And I think part of the reason why we do this is effectively what you're doing is this E factor here is too small for these islands. Basically, essentially, you can either as increasing the variance or increasing the efficiency factor for these islands, for those grid points specifically. And the physical justification is that these islands, the characteristic wavelength of these mountains is 5 kilometers, 10 kilometers, even less than that. Whereas in general, the scheme overall assumes a wavelength of, let's say, 80 or 100 kilometers.
If you found an analytic example for a triangular mountain, single mountain, won't it make more sense to plug in the formulae that you get from the single mountain, even if it's a long shape?
It would give you, probably give you, at least for which is basically, which is a Gaussian mountain, that would get better.
And has it been attempted?
Not to my knowledge.
Okay.
It could be.
Open for few additions.
Okay, thank you.